So welcome. So today we're going to do the electrical potential and electrical potential energy. And I think last time I tried to set us up with some groundwork, but let's just review that a little bit. So far we've done the electric force, which is measured in newtons. And then we decided that, and that basically, let's have a look at this. So Fe was equal to some constant times one charge times another charge over r squared. And then we said, well, that's fine, but supposing I want to look at the influence caused by the big charge without having the little charge there. Then I invent this thing called the electric field, which is measured in newtons per coulomb, which is basically this guy. And then we just say, well, imagine we don't have the little q there, so the big Q is still there. That's the one that's setting up the electric field. And so everything else is the same. And if you want to go between these two guys, if I want to go from the electric field to the electric force, I just multiply by Q when you think about it. Yeah. If I want to go the other way, I divide it by Q. You know, it's just how you do it. Yeah. And when I started thinking about force and mechanics, I remember the next kind of thing we did was work. And work was force through a distance. And so I'm going to start, and remember that the work was equal to the change in energy of the system. Potential energy, we had the work kinetic energy theorem, but we also could have work potential energies. You know, whatever work you do, that energy is stored in the system. So in electrostatics, we tend to talk about potential energy because we think of it as static. So the motion has stopped. So work potential energy theorem seems to be a good thing to think about. And my symbol for potential energy, of course, is U. And I'm going to go UE if you like. And what I'm going to find is if I take this force and I multiply it by the distance in line with the force, you know, etc. What I'll find is that I get something like basically KE QQ, because you need both things over R. And that kind of intuitively makes sense. I multiplied by a distance, so now is it the same distance? Let's not talk about that for a minute, you know, just. And then if I want to talk about, well, of course, now it's the work done on one charge by the other charge. Suppose I want this generic kind of like analogous to field. What would the work be if a 1 coulomb charge was the subject charge? You know, like what would the force be if a 1 coulomb charge was the subject charge? So I invent this thing, I don't invent it, but it's been invented, and it's called the electric potential, and this is basically KEQ over R. Now, to make things a little bit more complicated, so let's stop there for a minute. So we are talking about 4 equations that look somewhat similar. And if you just try and haphazardly study them, the chances are you'll get them confused. So the first thing I would really commend to you is trying to distinguish between these things. This is joules, and this is joules per coulomb. These are my units. Yes?
Sir, the first equation on the top is the potential energy?
Potential energy.
Work?
Equals work, but it is potential energy. And the one underneath is the electrical voltage. When you go and buy a 9-volt battery, this is the number they're talking about. This is the voltage. Yes?
So when we started with the electrostatic force equation, it was proximity of 2 charges. So 1 Q was 1 charge and 1 Q was the other charge.
Yeah.
But when you go to the field strength one, you keep the big Q and you drop the little Q. But on the other side, for potential, is that just arbitrary?
No, that's me just like said, well spotted. That's like, that's good attention to detail. I'm just like, messing up. Yeah, there's no significance in, I'm haphazard sometimes. Yeah, very good. And again, it's that, you know, this is the effect caused by the mother charge, just as the electric field is the effect caused by the mother charge. Yeah. So compare and contrast. If you think about it, the top row is two charges. So force and energy are two charges. The bottom row is only the mother charge. So field and potential, only one charge. And then if you look at it, the left-hand side is inverse square. So if I double my distance, I quarter the force. I quarter the electric field. Whereas on the other side, the potential and the potential energy, I have an inverse relationship. So if I double the distance between the point of interest and the mother charge, or the little charge and the mother charge, then I have half the effect. Yeah? So be careful. When I or you say potential, we've got to mean potential and not potential energy. We're not using a shorthand term, and that I think is often a source of confusion. So you've got to be slow down and be careful about, am I talking about potential energy or am I talking about electrical potential? And you've got to remember that just as electric field is quite abstract, so the electrical potential is quite abstract. Although we're very familiar with it because we buy cells, we get electricity out of the mains, and it's given to us in volts, you know. So we just got to be a bit careful with that. Then there's another divide. So I'm talking here about point charges. One charge, point charge, near another charge, a point charge. But there's another kind of area which is basically uniform fields. These are point charges. But then we have, and these are called radial fields. Then we have a uniform field. What we find is that the equations simplify when you get to the uniform field. So the way the book tends to approach it is that it teaches you about the point charges and then simplifies to get the uniform charges. And I was not taught it that way. I was taught it that you do the uniform and then you complicate it. I mean, that's in high school we did the uniform field and we got familiar with it. And then we said, let's look at things which are not so simple. And I'm moving towards that more and more. It's like it worked for me, and I sometimes see people not get an easy uniform field because they're confusing it with the complex point source field, point charge field. What makes it even a little bit more complicated, and this came up with mechanics and we kind of washed over it a little bit. In mechanics, when you learned that PE or UG is equal to MGH, and you learned that KE, UK if you like, is equal to a half mv squared, we were cheating like crazy. Because the question is the height with respect to what? Where are you measuring your height from? Wherever you're measuring your height from, that's zero energy. I don't know where zero energy in the universe is. Well, I do, but it's not obvious. And even more kind of like, less obvious if you like, is measuring your velocity with regard to what? The room? This room is traveling at 1,000 miles an hour because the Earth is rotating. It's probably traveling at 500,000 miles an hour relative to the center of the galaxy. We don't feel it. That was Aristotle's problem. He thought you could feel motion. You can feel acceleration. You can't feel steady motion. So we're traveling and we're traveling at some, whatever speed you like. You can measure our speed relative to an asteroid as long as the asteroid doesn't accelerate relative to us. So can you see how we cheated a lot? We just implicitly assumed a zero level and called the answer the absolute value, when really it's delta UG. The change in potential energy is this, and it's really delta UK. The change in kinetic energy is that. And so over here now, so then what happened is people started struggling with it, and they said, well, I do actually want to know the potential energy at the tabletop. And so recall that we took, when we were infinitely far away from all masses, or significantly far away from all masses, we call that 0 joules, and we went -1, -2, -3, -4, -5. We measured downwards in terms of joules. And it still means that when you go upwards, -2 minus -4 is +2. So when you're going upwards, you still get a positive change in potential energy, even though you're on a negative number line. It makes no difference. As long as the number line is pointing upwards, it doesn't matter if 0 is below you or 0 is above you. As long as you're going in the same direction, the differences work. So we have this weird situation where we have negative gravitational potential energy at any point, because it's 0 significantly far away. We do the same kind of trick with our electrical potentials as well. Electrical potential energies and our electrical potentials as well. So we can invent this thing called our delta UE and our delta VE. And our delta VE is going to be KE over R. KEQ. And then it's going to be 1 over R final minus 1 over R initial. And how do you go to get our UE? Do we have to learn a new equation for that? It's just KEQ 1 over R final minus 1 over R initial. With the negative, well, sorry, no, not with the negative sign. That's my next thing I'm going to talk about. Times Q. Yeah, remember, if you want to go upwards, you multiply by Q. If you want to go downwards, you divide by Q. So so there's not that many equations to learn once you know the pattern of how to get from one to the other. Until you know that, you've got 6 equations that are all vaguely similar. Yeah.
So that can be rearranged to look like the what's it, the K big Q little q.
Yeah.
Over delta R. Because it'd be R final minus.
Yeah. Okay.
Yeah. So
Yeah.
with the change in R.
Yeah. I suppose so. Yeah. Cool. Now, I mentioned signs here, and what we're going to talk about is when we roll a boulder down the hill. It's pretty simple. When you go downwards, you have a falling potential energy. So your delta UG would be negative to go downhill, yeah? It's more complicated with charges because we have positive and negative charges. Yeah. So we've got to be a little bit careful, and so what happens is we're just a bit more careful with our signs as I'll go through. There's negative signs in here that we'll talk about. But always draw the analogy of going downhill is going with the gravitational field, and as you go downhill, your potential energy decreases. Your change in potential energy is negative, yeah? That makes sense? High potential energy near the top, low potential energy near the bottom of a hill. If you roll a boulder down the hill, the change is a negative potential energy. Agreed? And think of the analogy of electric field lines go from positive to negative. Positive's like the top of the hill. The negative plate's like the bottom of a hill. So our electric field is like, I'm going to draw it like that. And a positive is like a boulder. So when a positive goes with the electric field, your change in potential is a negative. If an electron goes with the electric field, it don't want to go with the electric field. If the electron is going with the electric field, then it would be the opposite, because you're doing work to do that, so it would be positive. So signs are a little bit more confusing with this because we have both positive and negative charges. Think of positive charges as have been like boulders, and the electric field has been like gravity, and you can visualize very often. Okay. So with that, let's go through it. And I got to tell you, I've been trying to get this thing squared away for a while, so it's not quite there yet. So I take a bite from one side, I take a bite from another side, I take a bite from a third side. So it seemed like I'm saying the same thing over and over again, and I'm just trying to nibble away at this. So I want you, first of all, not to get confused about the definitions. So gravitational force is the force caused by the proximity of 2 or more masses. And I want you to get the analogies. So the electrostatic force is the force caused by proximity of two or more charges. And the gravitational force, the gravitational field strength is the gravitational force that a unit mass would experience. Now, here's the confusion. You don't need the unit mass to be there. It's what it would feel if it was there. Newtons per kilogram, and the electrostatic field strength is the electrostatic force that a unit positive charge would feel if it was there. Again, you don't need that second charge. Gravitational potential energy is the energy stored by a mass by virtue of its position in a gravitational field. And electrostatic potential energy is the energy stored by a charge by virtue of its position in a gravitational field. And then we have gravitational potential. We didn't really talk about it. I do mention it in Physics 1 these days. It's the gravitational potential energy per unit mass. It's what a 1 kilogram mass would have. It's the energy that a 1 kilogram mass would have if it was in that position near a planet. And electrostatic potential is the energy that a 1 kilogram positive, 1 coulomb positive charge would feel if it was at this position in an electric field. So try and get those really clear. What I see with this section is it's not the math that's hard, it's the definitions, it's the visualization that catches people. The math's not hard. And then equations that all look somewhat similar. So big M, little m over r squared, big Q, little q over r squared. And then that equals, well, that's going to be G big M over r squared, over m squared, times little m. So that guy goes away with that. And I'm sorry, I forgot my r squared. Excuse me. What a mess. Let me do that again. It's going to be big G, big M, little m over r squared divided by little m. So that goes away and that goes away. And then we have that unit vector in there. So 1 mass over r squared. And this is going to be similar. It's going to be big Q, Ke, big Q over r squared. 1 charge over r squared. And then we said for potential energy, well, potential energy is the amount of work that's done. And remember how we had work is equal to F dotted with dx? Do you remember that? F dot dx? We had the force times the displacement, but the displacement had to be in line with the force. And so we took the cosine of the angle that these two things differ in. There's our force, there's our displacement. We took that cosine of the angle to get the component of the displacement in line with the force. Do you remember that? So when we realized that if we work in vectors, that's a dot product. So the energy equals the integral of Fg, the force due to gravity, dotted with dr. And that gave us that. And so we have electrostatic potential is the integral of... Now, why is it an integral? Because as you go further and further away from the planet, the pull of gravity gets less and less, so the Fg gets less and less. So you can't just have a constant Fg. Same thing goes for this. As you go further and further from the mother charge, you get less and less force. And so you've got to integrate over that. And then we define our potential, and we just say, well, I'll take that potential energy and divide it by the mass, the little mass. And take your electrostatic potential energy and divide it by the little charge. So I'm just trying to get more and more familiar so that these forms become pretty helpful. So this is actually quite useful, just knowing that units are your best friends. So newtons for electric force becomes newtons per kilogram for a gravitational field strength. Joules, gravitational potential energy becomes joules per kilogram for gravitational potential. Newtons becomes newtons per coulomb. Joules becomes joules per coulomb, which is named after volt. Named that just to call the volt. Cool. And flogging a dead horse. This is probably overkill, but so we have electrostatic gravitational force, we have our gravitational field strength, we have our gravitational potential energy, we have our gravitational potential, and then here, I'm sorry, I didn't line this up very well. So we have the electrostatic potential energy, and we have the electrostatic, and then we have electrostatic potential. And I decided here to talk about, well, the difference between these two. And so we integrate this between 2 points, and we'll go through that. Okay. So there's 6 things in the end we're going to talk about. Force, field, potential energy, potential energy difference, potential difference. Okay. Visualization, you can think of this as being like a map, and you have a point here, and you can say to yourself, oh, what happens as I take that point from one place to another? Or I can have a charge here and say, what happens as I change that charge from one place to another? So big Q is somewhere different. I'm going to put it down there. It's not there, but big Q is somewhere else. Big Q is causing this electric field. So this is kind of different. Now we're causing the electric field, and now I'm saying, oh, in my potential energy and my potential energy difference, I'm taking a charge. There's my potential energy at that point, and my potential energy difference is taking that charge from there to there. That's little q, that's little q. But my potential and my potential difference is taking the point of interest and moving it from there to there. So you see the difference. This has got a charge that's playing around inside an electric field, and this one has a point of interest that's playing around an electric field. And that's where people get confused all the time. There's a lot of little details here. So be very clear. Step back and say, what am I doing here? Because then it becomes, I think, a lot clearer. I'm still working on this. You can see it's not typed out, but it's kind of like, if you want to go from electric force to electric field, what do? We divide it by Q2. If you want to go the other way, multiply. If you want to go from electric potential to electric potential energy, you divide by Q2. If you want to go from electric force down to electric potential energy, you integrate over R. If you want to go from electric field to electric potential, you integrate over R. Yeah, you multiply by R, basically, if it's constant. And this is another version of it where I'm just trying to, and I'll get a full version of this, which is all worked out. But don't lose track of this, because this is like, you know how to do this stuff. Frankly, with the point charges, you're just responsible for knowing the equations in the end. With the uniform charges, the equations are much simpler. So that's what you're going for. So there's 2 approaches. The one is that I'm going to take point charges and I'm going to try and figure out what's going on at a point of interest, whether I put a charge there or not. So these guys are setting up electric field, and this guy is responding to it. This could be Q. Or I could not have that Q there and have my point of interest. Alternatively, I could say, what's the effect of these charges? And draw out the electric field and have my point of interest, or put a charge there. Can you see there's a fundamental difference between the 2 of them? And the field, actually, if you know the field, it makes life a lot easier. So that's what we're going to do. Final little thing, electrical potential is just the potential energy over Q. I'm just, this is interesting. That's a really useful trick. If electric field can be measured in newtons per coulomb, as we'll find out, it can be measured in volts per meter. We'll find that out at the end. Two equivalent units for the same thing. And then the other one is the electron volt, which you've probably heard of. It's just a way of, if voltage, what are the units for voltage? Joules per coulomb. Multiply it by the charge of an electron, which is in coulombs, and you get joules. It's kind of nice. It's a very small unit of energy. It's also very convenient, because if I have electrons and I accelerate them through 100 volts, 100 EV is their energy. Boom. I'm done. It's an energy. It's not SI. Well, it maybe is SI. I don't know if SI adopted it, but it's not joules, but that still works. So in that area of science, they just work in EVs. They don't worry about joules. This raises an issue, and so it's going to come up again, but so we represent charges with Q, but their units are in coulombs. And later on we're going to use C for capacitance. It's going to get confusing. So again, you got to be real, slow down and be careful with yourself. This is not hard. You do stuff far more complicated than this. You've done stuff in the past that is far more complicated than this. The problem is it comes so quickly. And if you get involved in the complicated stuff, you don't really get the simple stuff, and so you make mistakes that you could easily avoid if you just step back a bit. You get lost in the woods. You know, you see all the trees and you don't know where you are. I've been through that. Okay, yeah, okay. We're going to start off with a uniform electric field. So, okay. Ironically, I'm going to use anyway, yeah. We're going to start uniform electric field. How do I know this field is uniform? What's the telltale sign that tells me this field is uniform? Sorry? The two arrows are parallel. Yeah, that's what tells me. Good. So uniform electric field, and we're taking a point of interest up here, and we have a point of interest down there, and we're moving a charge, a little q, from A to B. So if it's a positive charge, it's a boulder rolling downhill. We say if the electric field is uniform, forget about the previous equations, but we've seen them a while ago. Consider a uniform field directed along the negative y-axis. Consider the potential difference between points A and B. We're going to talk in terms of potential difference, and then we'll talk in terms of potential. Why? Just because it's easier. That's the more natural thing. When we talked of MGH, we were talking in terms of gravitational potential difference. We just lied about it, you know. So we know the generic term, which is the change in potential is equal to E dotted with ds. That's the force per coulomb multiplied by the distance gives me the energy per coulomb, which is potential. Okay, I can live with that. Let's expand this guy and make it, you know, more compatible to magnitude. So we know that this becomes E times the magnitude of ds times the cosine of the angle between them. And when I look at my D vector, which is basically that guy, and I look at my E vector, it seems to me the angle between them is 0, which means the cosine of 0 is 1. So it goes away. So I end up with the integral from E to ds, E times ds. If E is constant, which it is in this case because it's a uniform field and ds is a certain length, then this is just going to simplify out. We say E is constant, take it out of the integral. We say the integral from B to A of ds is simply that distance d. So ED. That's the take home. Delta V is equal to ED. Now, why is it negative ED? Because we're going downhill. Remember, if a positive charge goes with the electric field, it's a boulder rolling downhill, and when you go downhill, you have a negative potential. So I learned it, but I also get where it's coming from, so my memory's helped a lot.
So if it was going uphill, it'd be
Positive, yeah. So do you need to know all this stuff here? I think it's useful if you're going to use this over and over again, and certainly it will always be at 90 degrees in line with it. It will always be parallel to. The change in potential energy per unit charge is the force per unit charge times the displacement that the force moved through. This makes sense. Note that the electric field line's in the direction of lower potential. If I wanted to have delta U, the change in potential energy, what would I do? Yeah, that's when basically I got to take into account this little q. I've ignored this little q. Sorry, I got a thing on there. I ignored this little q all the way through it. I just said I went from that point to that point. Now we're putting a charge there, so I multiply by q, which equals minus QED. Quite easily done. I remember as a high school student learning that. Quite easily done. Oh, that's quite easily done. You know, when I was taught math, I don't know if you guys were, but when I was taught math, at the end of each math problem, we'd have to put QED next to it. It's actually some Latin thing that means something that they never told us about. So this like 60-year-old teacher was teaching me to write some Latin script down, which he never told me what it meant, and I'm teaching you to write something down, and I'm corrupting it and pretending it's English, you know. Quite easily done. That's what we all said. Oh, that was quite easily done. That's how I remember it. Yeah. Okay. Let's make it a little bit more interesting. Oh. What am I doing? Oh, I'm just doing what I said. Oh, look, let's make this delta U. Oh, we have to take into account this charge. Oh, look, we did it. Okay, so that's like no need for that. So let's make this a bit more interesting. Now we're not in line with each other, but we've already done this. My change in potential is equal to minus the integral of E dot ds, which equals minus E, because it's constant, electric field multiplied by the integral of E dot ds. And the integral of E dot ds, oh man, I kind of cheated there, didn't I? It's going to be E dot ds integral is equal to the E times ds times the cosine of the angle between. And now the angle's not 0, so there's the angle. So I could find this by taking that. I could find this by taking that electric field and multiplying it by that distance multiplied by the cosine of the angle between. Do you remember that? We played games with this all the way through mechanics. Yeah? The other alternative is that I leave it in vector form. It's not E. This is not E. He's a different thing. Yeah, different vector. It's just whatever we choose to call it, and we could call that D. Yeah. So basically, what we say is that this is just, well, because it's a constant electric field, we can take it out of the integral, and then the total thing is that. So basically, if I call this a vector, and I call that a vector, just do the dot product of those two. And we had that before in mechanics. Agreed? And if I want to find the electric potential energy, just multiply by Q. Let's say that I don't go down the hill at all. I just go across the hill. So again, you know, my change in potential is equal to minus E, because it's a uniform field, E dot S, which equals E times S times the cosine of 90. Cosine of 90 equals 0. So that would be 0 volts. Bad. I should have put a unit down. 0 volts. So it doesn't cost you any energy to go perpendicular to the electric field lines. Oh, I shouldn't draw it. I'm suddenly doing non-uniform fields, and I'm in a uniform field section. Okay. So what did we learn so far? I suppose we've learned that delta V is equal to the minus the integral of E dot ds. And what we learned is for uniform, this is for radial, let's say. Non-uniform, non-uni. And it simplifies and uni. It's for both. And it simplifies for uniform fields. We get minus ED. Yep. Or minus AD cosine the angle between, which equals minus E dotted with D. So I can talk about it in terms of vectors. I can talk about it in terms of magnitudes. And the thing I remember always is that my delta U equals Q times delta V. So I don't even need more equations for that. Yes?
Sir, I just make sure that S is from A to B, also here.
So in this one, S would be, well, in this case, no, S is from there. That's S.
Okay.
Yeah. Because it's 90 degrees. That's 90 degrees, yeah. Let's just reinforce. I'm pressing the wrong thing, sorry. Let's look. Yeah, okay. So let's have a look. We have a uniform E field, 7 newtons per coulomb in positive x direction. Let's draw it. Can you figure that out for me, please? Gonna- Can you pick?
What are we considering for?
You're moving, you're taking your point of interest from A to B. Oh, so, well spotted. So, vote when you got an answer. Oh, grab your things.
A and B are the same.
What do you mean A and B are the same?
They both say negative 42 volts.
No.
No, B's 24.
A and
Alpha
D.
and delta.
Oh, I thought you said A and delta. First and fourth.
I'm confused.
First answer
A,
choice.
the
alpha
and
choice
the-
and the delta choice.
they're the same.
Oh, A and D. I'm sorry, I thought you said B.
My bad.
I was going D. So, what does that tell you? Thank you, though. No, I thought you said B. I was going, oh, is he dyslexic? I'm thinking, is he dyslexic? And no, I'm deaf. Oh well, never mind. I was at my daughter doing Girl Scouting stuff this weekend, and she's 12, and she's like, we're at the stage where I kind of embarrass her a little bit sometimes. I don't mean to, but my presence sometimes embarrasses her. And we're walking down the street, and she's talking to me, and she says, just put your hearing aids in, Dad. Okay, I went back in the house, got my hearing aids, and I tend to forget them sometimes, because I can hear everything that I'm thinking, you know. How are we doing? 10. Come on. 6, 7, 8, 9, 10. Oh, yeah. So that's not so bad. Oh, we got it. Yeah. Well done. So stop it. Let's vote. Yes. Yeah, it's going to be. It's not so bad, is it? It's just basically, we can turn around and say that delta V is equal to minus E dotted with S, which equals minus E times S times the cosine of the angle between. So delta V is equal to, what does that equal? It equals minus E is 7 and S is 6, and it's cosine of 60, which is a half. So delta V is equal to 6 sevens are 42, and a half of 42 is 21 volts. So not bad. Let's make it a bit more interesting.
Quick question.
Yeah.
Will we see the 7 newtons coulomb? Will that sometimes be negative, or what?
The electric fields can't be negative.
So
it's the magnitude.
So we're never going to get a positive answer. Like how would we get a positive answer in this type of problem?
From B to A.
Yeah.
So
So
if you ask is B to A.
B to A.
Okay, gotcha. Yeah, so you reverse the vector. Yeah, gotcha.
Yeah, reverse the vector. Yeah.
If you move from B to A, you get.
I mean, if your vector would be like that, that would be a B, that would be a D, and that would be a E. So if you like, your angle would be
The cosine of that would be a
90 plus, what would that be? I should know this. 90 plus 30, 120. And that would give you the negative, which gives you the positive. Yeah, yeah. Cool. Good question. Ooh. Ooh. Got to do my sums, haven't I? Oh, it's going to be a real pain, as you guys can see. Not so bad. And E. Oh, I didn't record any of that. Oh, no, I did. Pause. I'm sorry. So let me, I just need to step back for a second. So I just didn't record this, so let's record it. So we had, there's one vector, there's the other vector. I do the equation, it's q times delta v, which is q times this dot product, and then I work out my dot product. So I'll leave that for people on the tape to look at. And then what I said was, let's go back and let's do the non-uniform field. So here we have a situation where we're starting off at A, and we're going to B. Now, this is a positive charge. So am I envisaging a sinkhole or a volcano? It's a volcano, isn't it? And am I going nearer to or further away from the volcano's peak as I go from A to B? Further away. So am I going uphill or downhill? Downhill. So will my potential increase or decrease? Decrease, because I'm going downhill. So that all kind of makes sense. And I'm going to imagine this little incident in time when I'm in this particular position. It's defined by that unit vector. It is that far away. And I have not the total length from A to B, because I can't work with that anymore. I've got to do a little bit of length. So that is my little bit of length there. And I've got to try and do the math on that. Things are changing on me. So I say, well, my change in potential is equal to minus the integral from A to B of E dot ds. That's my basic equation. Now, the integral of ds means I take all these little bits of length and integrate them rather than taking the total length and calling it S. You know, that's the bit I'm doing. And I know that my electric field at any given point on this diagram is equal to the Coulomb's constant times Q, which is the mother charge. I called it little q here, just I don't know why. Over the distance between the mother charge and the point of interest, r squared, times a unit vector pointing in that direction. And so I know that from Coulomb's law, basically. And I know that E dot ds must equal then, let's substitute in, E times Q over R squared. This is the vector bit, the unit vector, so it's R hat, the unit vector dotted with ds. Now let's have a look at this. So R hat is pointing in that direction. And we say, well, hold on. The unit vector has a magnitude of 1. ds has a magnitude of ds, and the magnitude of this dot product is equal to 1 times ds times the cosine of the angle between them. And if I draw this out a bit better so you can see it. So there's my ds, and this is my theta in there. So it's 1 times ds times the cosine of the angle between them. Well, actually, this is a right triangle. I'm going to define this as a right triangle and make this final thing that length. I'm going to call that dr. So now I've defined a right triangle, and what I know is the dr, the adjacent divided by ds, is the cosine of this angle from simple trig. So dr is equal to ds cosine theta. Okay. Well, I have ds cosine theta there. So this means the E dotted with ds is equal to ke q over r squared times 1 times ds cosine theta, which is the same as ke q over r squared dr. Oh, okay. That's nice. Because what I do, there's dr on my diagram. And there was ds. Oh, so I just change this into a radial form. And I say, well, delta v equals minus the integral of E dot ds, which equals minus the integral of keq over r squared times dr. And I know how to do that. That goes to r to the minus 2. Increase your power by 1, put it in the denominator. That's minus 1 over r. So then I write it out in the expanded form. Delta v equals keq 1 over rb minus 1 over ra. Now, remember, minus and minus make plus. So that negative sign has been incorporated in this. So this is a positive value with the negatives in there, yeah? So I've not forgotten that negative sign. I incorporated it, okay? That's just wrinkle, just believe the equation. What is the potential difference between a point that is 3 meters to the north of a 2 Coulomb positive? So here's my 2 Coulomb positive, and this is 3 meters. There's my P, if you like, my PA. And second point was 6 meters to the south. Oh my word, opposite direction, 6 meters, PB. So what is my potential difference? My delta V is equal to KE times, what was it? Q 1 over R final minus 1 over our initial, yeah? Which equals KE times Q is 2, it's plus 2, times 1 over 6 minus 1 over 3. Got to get those the right way round. So delta V is equal to KE times plus 2 times 1 over 6 minus 2 over 6, which equals, and this is me bad teaching, because I shouldn't make it so that when I subtract them I get one of the original values, because people can interpret that in a whole bunch of ways, but I'm just subtracting them. So I get KE times positive 2 times minus 1 over 6. So delta V is equal to minus 2 over 6 KE, which equals minus 0.33 KE. What are the units going to be? Volts. Yeah. Put that in brackets, put it in a square. In a test, I have no problem with you leaving the KE. I'm finding on occasions that people are leaving me with more math than they have. They're leaving me with square roots, and they're leaving me with 1 over somethings and all that, and that's not acceptable. So bring it down to a fraction, to a you know, what's this called? A decimal. Yeah, bring it down to a decimal for me, please. There'll be times when I say write an expression for, and that's different, but by all means leave the KE in there. Did the direction matter? Does it matter? So watch out, because I will try and engage you by saying, oh, this is 15 degrees. This is 6 meters, 15 degrees to the west of north, and this is, you know, up the hill and down the valley. And if you get caught up in that, you're going to, you know, make what is a straightforward problem into a hard problem. And that's the physics bit. Yeah. Question, yeah.
How are we going to know exactly which one's going to be point A and which is going to be point B?
I got to tell you. You move, you know, this says partial difference between a point. Yeah. So that's an interesting point. Between a point, which is common parlance, doesn't tell you which way you're going. Yeah. So I can get around that by saying, what is the magnitude of? Then the sign doesn't matter. Yeah. Or I can say, considering a point of interest moving from one to the other. Yeah. But I've got to be specific on that. If I'm going to hold you to account for the sign, I've got to be specific for that. I can't just be, you know, haphazard with it. But you're right. Okay. So we know how to do the potential difference for a point source. We know how to do the potential energy difference, just multiplied by Q, yeah? What about the potential? And what we do here is we do the trick we did before, where we say, oh, let's call infinitely far away from any charges or significantly far away from any charges 0 potential. So what we do is we do this same thing. We imagine bringing this point of interest from infinity to there. And so our initial distance was infinity, which means it goes to 0 because it's 1 over infinity. So we end up with this very simple form. That's kind of nice. And it's an inverse relationship. So what is the electric potential of a point that is 3 meters to the north of a plus 2 coulomb? 2 coulomb positive. I am 3 meters to the north. There's my point of interest. I want to know my potential V, not delta V. V. So what I say is delta V is equal to KEQ 1 over R final minus 1 over R initial, because every time I write it down I learn it. V is equal to KEQ 1 over R. See where it comes from. V is equal to KE plus 2 times 1 over 3, which equals 0.66 KE, and joules per volts, joules per coulomb. Cool. I have to stop in a second. I can bring these things together and add them. I'm going to stop now because otherwise this is going to